All right. Day 2 of our continuities, again, kind of focusing on discontinuities to decide if something is continuous. The first thing I want you to start with is this. We now have looked at a couple things like what makes a function exist, what makes a limit exist, and I want you to work with your table partners and see if you can come up with some options here. With your table partner, draw a function that would satisfy the first one. F of -1 exists, but the limit at -1 does not exist. F of -1 exists. The limit at -1 does not exist. So think through what makes a function value exist, what makes a limit exist or not exist. See if you guys can draw a picture, and there are multiple correct answers here. What makes a function have a value somewhere? Closed dot. So I would make sure we have a closed dot at -1. There are a couple options for this next answer. What makes our limit not exist? A jump discontinuity. What else could have happened there? A removable. Does that make our limit not exist? That would give us a function value maybe, but our limit would exist, and that doesn't match what's up here. The two functions need to be at different y values. There was something that would make our limit not exist that wouldn't have meshed well with this. How about your infinite discontinuity? Also makes a limit not exist, right? Because it would be headed towards maybe infinity, negative infinity, but we need a function value there. So going back to the first suggestion, a step function or a piecewise function would work best here. And we need to have one of those have a closed dot at -1. This is where we all could have a very different picture, but one of my functions needs to have a closed dot at -1. One of my functions needs to have an open dot at -1. So that my left and right hand limit towards -1 do not match. That satisfies the second part of it. Limit does not exist. The function value does. Yes. No, and it's actually not a function either because it fails that vertical line test. Yeah. So we wouldn't actually see that because all of these are supposed to be functions. So in that umbrella of functions, and it doesn't fix the whole discontinuity thing either. Yeah, good question. All right, let's try another one that's similar to this. This time I'm telling you that f of 2 exists. The limit at 2 exists. But the function is not continuous. So draw me a picture where all three of those things would be true. The function value exists, the limit exists, not continuous. All of that's happening at +2. So again, go back to your definitions of what has to happen for a function value to be there, what has to happen for a limit to be there, what has to happen for it not to be continuous. It seems like a lot, but once you kind of figure out what to draw, it's a pretty easy explanation. Let's start at that end part, not continuous. Which type of discontinuity did you have to pick for this one in order for the other two things to be able to be true? A removable discontinuity. Because in removable discontinuities, the limit exists. We have a function value that does not match that. And that's all happening at 2, and that's what made it discontinuous. So we would have a removable discontinuity with a value somewhere else. Close that to make it have a value, a limit in the right and left that head to the same spot, but an open dot there so that it is not continuous. Questions on any of that? All right. Going back to what it means to be a continuous function, that means that we have values and our limits match at all points along our domain. Given this one, it asks us to create this so that it is a continuous function. And it's a little confusing at the beginning here because there's a lot of variables going on, but basically we're trying to find some number that we can plug in there for A so that this will continue to be a continuous function. Now, if you look at each of those individual functions, x squared minus 1, that's, if I were to just draw that all the way across my graph, that's a continuous function, right? There's no domain restriction on that. Same thing with this one, just 2ax, a being just like another number, so like 2x, continuous function, right? The discontinuity could potentially happen when we flip between our two equations, making it that piecewise, if the piecewise doesn't join up, it's not continuous. So what we need to do is pick out A so that the two pieces will join up right there where it flips between my two equations. Is that all making sense so far? So really we're focusing on this particular x value where it flips between the two functions. And what I need to happen at that point when x is 3 and flips between the two of those, I need these two to be equal to each other so that the values are going to mesh together, or my limits are going to come together at x equals 3. So what I'm going to do is I'm going to take that value and plug it in for x and say that I need these to be equal to each other because that allows me then to figure out what a value will work for that. So wherever there's an x, I'm going to put in a 3, again, because that's where I flip between my equations. And that will help me figure out, in order for those two to come to the same spot at 3, what a value that would have been. So let's see, 3 squared is 9, minus 1 is 8, 2 times 3 is 6. If I put an a value of 4/3 in here, this will be a continuous function. Questions on that? No? We're going to do one just a little bit more challenging, but along those same lines. Same idea. Find an a value so that this is a continuous function. Now, it's a little bit more complex and a little bit less complex because we do run into a domain restriction up here, but notice the other function is literally just a. So when I figure out what this needs to equal, that's what a is going to be, right? But here's my problem. If I were to follow the exact same steps that I gave you on the last page, that said plug in the number where we make our decision between the two equations, because that's where the potential discontinuity is going to happen. If I plug that in for x and set these equal to each other, first of all, this function is just a. And when I plug 2 in here, do you see what issue I'm running into? We get a 0 in the bottom of our fraction, right? We get an undefined. So they're not giving me a value. So go back to some strategies we have. When I wanted to do direct substitution into something like this and I wasn't able to, what did we do? Factored and simplified, right? You can employ the same strategy here. See if you can simplify out that domain restriction issue that we're having. So before I sub in, because the subbing in is not working at the moment, I'm going to factor and see if I can simplify. And when I do that, the issue I was running into all of a sudden is no longer an issue because I've simplified out the x minus 2 in the bottom. And now I'm left with x plus 2 in the top. Now I can sub in for x the value that we were looking at, specifically at x equals 2. Four would be the value I would need there in order for that function to be continuous. Any questions on that? All right. The last topic we have today, guys, is a huge, huge, huge theorem that we have in calculus called the intermediate value theorem. It shows up over and over. Okay, so in fact, it shows up so often that we will abbreviate it, IVT, always, because we're not going to sit here and write out intermediate value theorem, and we use it that often that we want an abbreviation for it. Okay, so the intermediate value theorem says this. A function y equals f of x that is continuous, and I'm going to kind of highlight some of the important things. When we want to use the intermediate value theorem, we have to guarantee these things are happening, that it is continuous on some interval. Okay, so on the interval that we're looking, it must be continuous. Takes on every value between f of a and f of b. What we use the intermediate value theorem for typically is to show that some other answer is going to be guaranteed to happen on that interval. I'm going to put some numbers out here because I do think that the variables become distracting, and I don't want to distract us here with our variables. And so to understand it, I'm just going to put some sample numbers out there on our picture. So if I were looking at this picture, and let's say that we want to look at the interval from, let's call this, instead of A, we're going to call it 1, and instead of B, we'll call it 5. Okay, so we're looking at the interval on the x-axis from 1 up to 5. And we've got some function f of x. And when I plug 1 into that function, I get some y value, right? This point right here, I get some point right here. That is some answer. Let's say that that's what, like 2? I don't know, kind of looks like 2. And then when I plug 5 into my function, I get some other y value way up here. Did I say that was 5? Let's say when I plug that in, I get 10. Okay. What we can use this for is to guarantee that any value that happens between 2 and 10 will also be on my graph because it is continuous. So as I trace my graph from 1 to 5, I hit every single y value that exists between 2 and 10. And so what I can say is, I don't know which x value it is between 1 and 5, but there will be some x value on there, call it c, that will give me some whatever number this is, let's say 7, as an answer. So somewhere in the interval between 1 and 5, there exists some c, some number c, in which I would get the answer 7. Because 7 is between 2 and 10. And because it's a continuous function, I have to hit every number between 2 and 10 on the way. That's what the intermediate value theorem is telling you. So one of the examples of ways that we will see that, a lot of times will involve like a table of values. And in that table of values, what we're looking for is our y values that cross over whatever y value they're asking us to identify or to prove would exist. Okay? So we're looking at on this one, this function, f of x equals that up there. Now, first of all, given that function, I can say that it is continuous knowing what I know about functions, right? It doesn't have a domain restriction. Agreed? It's not a fraction, a radical in the bottom of my fraction, logarithmic equation, anything. So I know that is a continuous function. That is going to be important. Every time I want to use the intermediate value theorem, I must cite the fact that it is a continuous function. So because f of x is continuous, and they are asking me to look at this interval from -2 to 2, which is kind of like this table right here. So -2 to 2 would be about from here to here on this table, okay? They're asking me how many times can I guarantee that I would see the number -1 show up. Okay, so where do I look? Well, the x's are going to be my interval. The y values are where I'm looking for -1 to show up, but what I'm really looking for is when is it going to have to cross over -1. So on here, for example, -2.875 is lower than -1. -1.625 is bigger than -1. So if I go from something smaller than -1 to something bigger than -1, aren't I going to have to cross over -1? That's what we're looking for, is the numbers that will sandwich -1. One smaller, one bigger. It doesn't matter the order, but as I connect those two in my picture, I would have to have crossed over -1. So I know that -1 will fall somewhere between those two. So I can guarantee it one time right there. And then I just continue looking at pairs as I go and find all of the pairs that are going to cross over -1. So this one is currently bigger than -1. So I look at the one next to it. -1.375. Is that smaller than -1? Yeah, so it's going to have to cross over -1 again right here. So I know between those two numbers, somewhere between those two numbers, it's going to be -1. So then I check one more time here. From -1.375 to 0.875, is it going to cross over -1? Smaller than, bigger than. And that's what I look at. Is one smaller and one bigger? Yes, then it is going to cross over -1 one more time along here. So how do we use this? We would say because f of x is continuous on -2 to 2, on the interval -2 to 2, the intermediate value theorem says there exists some c such that f of c equals -1 at least 3 times. You're going to want that. Okay, so the important things. Now there's not a lot that's not important in there. I have to identify that it is continuous on the interval. I have to cite the intermediate value theorem. I have to identify how many times that it's going to be that particular number. Now, as we get used to this, our free response questions, which an intermediate value theorem question is an incredibly common free response question. Okay, typically will be about a 3-point question. One that you cite the requirements for it working in the intermediate value theorem. Continuous on the interval. That you cite the intermediate value theorem, and that you correctly identify how many times it can be that value. Those are typically the 3 points that go with an intermediate value theorem question. So when you use it, make sure that you do those things. It's continuous. Intermediate value theorem tells me this. This is how many times I'm going to see that number. Okay? You'll see some other things off to the side. Those are typically not needed, but like maybe citing those exact values, things like that, to kind of support your answer as you guys look like at my work and such. But typically those are your 3 points you're going to see on an intermediate value theorem question. Any questions on this? All right. I do need you guys to get out your Chromebooks. Your homework is here, and we are going to take a homework quiz. When you are done with your homework quiz, you may get to working on your assignment.